Right now, as you sit there watching this, entire universes could be brushing against ours in ways we can't even begin to perceive. The very fabric of reality might be folded into dimensions beyond our senses, hiding secrets that could rewrite everything we know about existence. This isn't science fiction, it's cutting-edge science. For centuries, we've lived under the illusion that our three-dimensional world is all there is. But what if space itself has layers we've never seen? What if the reason gravity seems so weak is because most of it is leaking into these hidden dimensions? Today, we're going to peel back the curtain on reality itself. We'll explore 30 extraordinary theories about these unseen dimensions, from the mind-blowing mathematics of string theory to radical ideas that blur the line between physics and philosophy. Some of these theories are backed by equations scribbled on blackboards at the world's top universities. Others will challenge everything you thought you knew about the universe. One thing's for certain: by the time we're done, you'll never look at the space around you the same way again. Now let's dive into the first and perhaps most famous theory about hidden dimensions, string theory's 10-dimensional framework. Picture this: everything in our universe, from the stars above to the screen in front of you, might not be made of tiny dots of matter but of unimaginably small, vibrating strings. These strings aren't just wiggling around in the three dimensions we know: length, width, and height. Instead, they require a 10-dimensional stage to perform their cosmic dance, 9 spatial dimensions plus time. Why 10 dimensions? It's not just a random number. It's the only way the math behind string theory works. Without these extra dimensions, the equations collapse like a house of cards missing half its foundation. But if these dimensions are real, where are they? Here's the mind-bending part. They could be curled up into spaces so tiny that even our most powerful microscopes can't detect them. Imagine an ant walking along a telephone wire. From far away, the wire looks like a simple one-dimensional line. But up close, the ant can move not just forward and backward but also around the wire's surface, a hidden second dimension compactified into a microscopic loop. This compactification idea isn't just a fanciful analogy. It's how physicists explain why we don't notice these extra dimensions in everyday life. They're folded away at scales a billion times smaller than an atom, invisible to our senses but essential for the string's vibrations. Those vibrations aren't random either. Just like different vibrations of a guitar string produce different musical notes, the way these cosmic strings vibrate determines the properties of particles, electrons, quarks, even the carriers of forces like gravity and electromagnetism. Speaking of forces, string theory's extra dimensions might hold the key to one of physics' biggest mysteries: why gravity is so weak compared to other forces. It's baffling. A tiny fridge magnet can defy the gravitational pull of our entire planet. But what if gravity isn't weak? What if most of its strength is leaking into these hidden dimensions, diluting its effect in our familiar three-dimensional world? That would mean gravity only seems feeble because we're missing the full picture, like trying to hear a whisper in a thunderstorm. This isn't just abstract theorizing either. While we haven't yet found direct evidence of these dimensions, particle colliders like the Large Hadron Collider are hunting for clues, tiny energy signatures or exotic particles that could hint at their existence. So the next time you drop your phone and it falls to the floor, remember, it might not just be gravity at work, but the invisible tug of dimensions we've yet to fully understand. And with that, we're just scratching the surface of what these hidden layers of reality might reveal. But let's take this one dimension further, literally. If string theory's 10 dimensions left your head spinning, hold on tight, because M-theory cranks it up to 11. Think of it as the grand unified theory of strings, a cosmic glue that ties together 5 competing versions of string theory into one elegant framework. Physicists sometimes call it the mother of all string theories, and for good reason. It doesn't just add an extra dimension like an afterthought, it fundamentally reshapes how we picture reality's hidden layers. So what's so special about this 11th dimension? Picture the dimensions we've discussed so far as threads in a tapestry. M-theory suggests that some of those threads aren't just strings, they're vast, stretchy membranes, or branes for short. These aren't the biological membranes you'd find in a cell. Instead, imagine them as enormous cosmic sheets floating in higher dimensional space. Some could be as large as entire universes. In fact, our universe might just be one three-dimensional brane drifting in an 11-dimensional sea, with other branes hovering nearby, each potentially hosting its own parallel cosmos. Here's where it gets wild. If these branes exist, they might explain why we've never detected extra dimensions. Our entire observable universe could be stuck to one brane like a piece of dust clinging to a soap bubble. Gravity might leak off our brane into the higher dimensional bulk, making it feel weaker in our world, just like how a flashlight beam dims when its light spreads into a larger room. Meanwhile, other forces like electromagnetism could be trapped on our brane, which is why they seem so much stronger by comparison. The implications are staggering. Collisions between branes could trigger big bangs, birthing new universes. Vibrating branes might generate gravity waves detectable across dimensions. And if other branes hold parallel versions of reality, they could be separated by less than a millimeter, just curled up in directions we can't perceive. Imagine 2 pages in a book. From the edge, they look stacked right on top of each other, but open the book and you see their worlds apart. Now, why haven't we spotted this 11th dimension yet? It might be sealed away at energies so extreme they dwarf anything our particle colliders can reach. Or perhaps it's hidden in plain sight, warped or compactified in ways we haven't even imagined. Until we crack the code, M-theory remains a tantalizing sketch of reality's blueprints, one that could rewrite everything from the birth of the cosmos to the fate of parallel worlds. And if it's right, we're not just three-dimensional beings in a four-dimensional universe. We're travelers on a membrane adrift in an ocean of dimensions we've only begun to chart. Now let's take this membrane idea even further. The Brane World Scenario flips our understanding of the universe on its head, literally. Instead of floating in empty space like we often imagine, our entire cosmos might be stuck to the surface of a vast, three-dimensional membrane drifting through a higher dimensional realm. Think of it like a slice of bread in an infinite loaf, where each slice is its own universe, and the spaces between them are dimensions we can't see. This isn't just wild speculation. The Brane World idea could solve one of physics' biggest puzzles, the hierarchy problem. Why is gravity so weak compared to the other fundamental forces? Picture this: gravity might not be weak at all. It could be just as strong as electromagnetism or the nuclear forces, but most of its influence is leaking into those extra dimensions, like water seeping through a sponge. From our perspective, trapped on our three-dimensional brane, gravity would appear diluted, as if someone turned down the volume on the universe's gravitational pull. But here's where it gets even more mind-bending. If our universe is one brane among many, others could be floating right alongside us, separated by less than a millimeter in a higher dimension we can't perceive. Imagine 2 sheets of paper lying flat on a table. To an ant walking on one sheet, the other sheet is invisible, even though they're barely apart. Now replace those sheets with branes, each potentially hosting its own stars, galaxies, and even life. Collisions between these branes could have sparked our own Big Bang, and future collisions might create entirely new universes. The implications are staggering. If other branes exist, their gravity could subtly tug on ours, leaving faint fingerprints in the cosmic microwave background, the afterglow of the Big Bang. Some physicists even speculate that dark matter might be ordinary matter trapped on a nearby brane, its gravity leaking into ours, and if branes can vibrate, their ripples might generate gravity waves detectable across dimensions like echoes from a hidden room. Of course, proving any of this is a monumental challenge. If extra dimensions exist beyond our brain, they could be curled up too small for our instruments to detect, or stretched so vast that their effects are vanishingly subtle. But if the Brane World Scenario is real, it would mean we're not just living in a universe, we're living on one. And out there, in the higher dimensional dark, entire worlds might be hovering just beyond our reach, separated by a gap smaller than a hair's width, but in a direction we can't point to. It's a humbling thought, one that turns the fabric of reality into something far stranger than we ever imagined. Now let's shift gears to a theory that turns the idea of tiny, curled-up dimensions on its head. What if some of these hidden dimensions aren't microscopic at all? What if they're as large as a millimeter across? That might not sound huge, but in the world of particle physics, it's massive. This is the bold proposal behind the theory of large extra dimensions, and it challenges one of our most basic assumptions about how gravity works. Here's the problem it tries to solve. Gravity is inexplicably weak compared to the other fundamental forces. Think about it. A tiny fridge magnet can defy the entire gravitational pull of Earth. Why? Traditional theories suggest gravity's weakness comes from its effects being diluted across tiny, Planck-scale dimensions so small we'll never see them. But what if the answer isn't in the size of the dimensions, but in where gravity's strength is coming from? Imagine gravity isn't confined to our three-dimensional space like the other forces. Instead, it could be spreading out into these large extra dimensions, thinning its influence in our familiar universe. Picture a garden hose. If water flows through a narrow nozzle, the stream is strong and concentrated. But if the hose splits into multiple wider tubes, the pressure drops. Gravity might work the same way. Its true strength is divided across these millimeter-sized dimensions, leaving only a faint trickle in our world. This idea isn't just theoretical gymnastics. It has real-world consequences we might actually test. If large extra dimensions exist, particle colliders like the Large Hadron Collider could produce telltale signs, tiny, high-energy particles disappearing into these dimensions, or even miniature black holes popping in and out of existence. So far, no such evidence has been found, but the search isn't over. Some physicists speculate that future colliders with even higher energies might finally glimpse these elusive dimensions. There's another fascinating twist. If gravity is leaking into large extra dimensions, it could explain why we haven't detected gravitational waves from the very early universe. Those ripples in spacetime might have dissipated into these unseen realms, leaving gaps in our cosmic records. Even more intriguing, some models suggest that dark matter, the invisible stuff holding galaxies together, might just be ordinary matter interacting with us through gravity's extra-dimensional reach. Of course, not everyone's convinced. Critics argue that if extra dimensions were this large, we'd have seen their effects by now. Others point out that the math gets messy when you try to reconcile this idea with quantum mechanics. But that's what makes science thrilling. Theories like this push the boundaries of what we think is possible. Whether large extra dimensions exist or not, they force us to ask deeper questions about the fabric of reality. And sometimes the most radical ideas are the ones that lead us to the truth. Now let's step back in time to one of the earliest and most daring attempts to unravel the mystery of hidden dimensions. In the 1920s, long before string theory or branes entered the scene, two brilliant minds, Theodore Kaluza and Oscar Klein, proposed a radical idea. What if there wasn't just a fourth dimension of time, but a fifth dimension hidden in the fabric of the universe? Their theory wasn't just about adding another direction to space. It was an audacious bid to solve one of physics' biggest puzzles, unifying Einstein's gravity with Maxwell's electromagnetism. Here's how it worked. Kaluza noticed something astonishing. If you rewrote Einstein's equations of general relativity to include a fifth dimension, something magical happened. The extra terms in the math looked exactly like Maxwell's equations for electromagnetism. It was as if the fifth dimension was weaving gravity and electromagnetism into a single tapestry, but there was a catch. Where was this extra dimension? Why couldn't we see it? That's where Klein stepped in. He suggested the dimension wasn't missing. It was just curled up into an unimaginably tiny circle, far smaller than an atom. Think of it like an ant walking along a garden hose. From a distance, the hose looks like a simple line, one dimension. But up close, the ant discovers the hose has a circular dimension wrapped around it. In the same way, Kaluza and Klein proposed that every point in our familiar four-dimensional spacetime might hide a microscopic loop of fifth dimension. The vibrations of this tiny dimension wouldn't just explain electromagnetism. They'd also create new particle-like excitations, early hints of what we now call Kaluza-Klein particles. For a while, this idea electrified the physics world. Here was a way to merge two fundamental forces under a single geometric framework, but problems soon emerged. The theory couldn't explain why the fifth dimension stayed so perfectly compact while others didn't exist. Worse, when quantum mechanics burst onto the scene, the math became unwieldy. By the 1930s, most physicists had moved on, and Kaluza-Klein theory faded into obscurity. Yet its legacy lives on, those compactified dimensions. They became the blueprint for string theory's curled-up Calabi-Yau shapes, the idea that extra dimensions could unify forces. It inspired generations of theorists searching for a theory of everything. Even the concept of higher dimensional vibrations foreshadowed modern ideas about branes and quantum fields. Kaluza and Klein's work was ahead of its time, a beautiful idea that failed not because it was wrong, but because the tools to finish the job didn't exist yet. What's remarkable is how close they came with the math of their era. Today, with supercomputers and advanced geometry, we're still chasing their dream of unification. Their story reminds us that sometimes the boldest ideas take decades or even centuries to find their full meaning. And who knows, maybe the next breakthrough in hidden dimensions will trace its roots back to those two visionaries and their tiny, invisible fifth dimension. While Kaluza and Klein imagined dimensions curled into microscopic circles, let's stretch our minds even further to a world where all dimensions might loop back on themselves, not just the hidden ones. This is the mind-bending concept of cyclic dimensions, where space itself could be finite yet boundless, like walking around a globe where every direction eventually leads you home. Imagine you're an astronaut floating in space with a laser pointer. In our everyday experience, if you shine that beam, it travels straight forever into the void. But in a cyclic universe, that laser light could theoretically loop all the way around the cosmos and hit you in the back after billions of years. This isn't just sci-fi. Mathematically, cyclic dimensions mean spacetime isn't an infinite grid but more like the surface of a balloon, where every path circles back. Unlike infinite dimensions that stretch endlessly, cyclic ones wrap around, creating a closed geometry with profound consequences. For quantum particles, this changes everything. Take an electron orbiting an atom in cyclic space. Normally, its position is a probability cloud, but in a looped dimension, those probabilities get tangled in knots. The particle's wave function must match up perfectly when it completes a full circle, like a snake biting its own tail. This forces quantum states to quantize, vibrating only at specific frequencies, like notes on a guitar string. Some physicists speculate this could explain why we see discrete energy levels in nature, from atomic spectra to the cosmic microwave background's faint imprints. Cosmologically, cyclic dimensions might rewrite the story of the Big Bang. If time itself is cyclic, our universe's birth could be just one phase in an endless cycle of expansion and contraction. Picture a slinky stretching and collapsing, each coil representing a new cosmic epoch. This idea, called conformal cyclic cosmology, suggests black holes in one era might seed galaxies in the next, with dimensions resetting like a cosmic heartbeat. Even spacetime's shape gets reinvented. Instead of flat or curved, it becomes a self-repeating tapestry where every end is a new beginning. But how would we test such a wild idea? One clue might hide in the night sky. If dimensions truly loop, distant galaxies could have mirror images visible in opposite directions, like reflections in a funhouse mirror. Astronomers have even searched for matching circles in the cosmic microwave background, ghostly echoes of a universe that's finite but has no edges. So far, no luck, but the search continues. What makes cyclic dimensions so captivating is their elegance. They offer a universe that's neither infinite nor static, but dynamic and complete in itself, a cosmic Ouroboros where geometry and physics dance in an eternal loop. Whether they're real or not, they remind us that the hidden fabric of reality might be far more intricate than straight lines and endless voids. Sometimes the most profound truths come full circle. But what if the dimensions we experience aren't even the full story? Shifting our perspective entirely, the holographic principle turns reality inside out by suggesting everything we see, every galaxy, mountain, and atom, might just be a three-dimensional movie projected from information stored on a distant two-dimensional surface. Picture this: you're watching a breathtaking IMAX film, completely immersed in its depth and movement, but the entire experience is actually encoded on a flat reel of film. The holographic principle proposes our universe works similarly. The math shows that all the information needed to describe every particle in our 3D cosmos could fit perfectly onto a 2D boundary, like the surface of a bubble enclosing space. Physicists Leonard Susskind and Gerard T. Hooft first realized this when studying black holes. They found a black hole's entropy, which measures its hidden information, doesn't scale with its volume but with its surface area. It's as if reality keeps its receipts not in filing cabinets but on sticky notes plastered to the walls. This wild idea gets concrete through something called the add/CFT correspondence. Without drowning in alphabet soup, this is a mathematical bridge connecting two seemingly unrelated worlds. On one side, you have string theory playing out in a warped higher dimensional space called anti-de Sitter space. Imagine a cosmic funhouse mirror where distances stretch oddly. On the other side, you have a quantum field theory living on that space's flat boundary. The magic: these two frameworks describe identical physics. A thunderstorm in the 3D bulk becomes a dance of equations on the 2D surface. It's like discovering the screenplay of your life exists as a pop-up book, every event encoded in simpler, flatter form. Where this gets cosmic is with black holes. The information paradox, Hawking's puzzle about whether black holes erase information, melts away if data isn't lost but merely transformed. Like burning a novel where the ashes still contain the words in microscopic patterns, a black hole's 2D horizon could preserve information even as the 3D object evaporates. Some theorists take this further, suggesting our whole universe might be the holographic fallout from a black hole in a higher dimensional cosmos. The implications scramble our intuitions. Your morning coffee, your smartphone, even the screen you're watching this on, all might be elaborate projections from a hidden flatland. It's as if reality has been running on cosmic Instagram this whole time, with 3D posts rendered from 2D data. While we can't peel back the universe's screen yet, experiments with quantum entanglement and lab-made holographic materials are testing the math. Whether the principle holds or not, it reminds us that dimensions might not be building blocks but emergent illusions. Like realizing the movie screen was the real story all along. Now let's bend our minds around something even stranger: dimensions that aren't just hidden but warped. Imagine spacetime isn't a flat sheet but more like a stretchy fabric, with hidden folds and curves that reshape reality itself. This is the heart of the Randall Sundrum models, where extra dimensions don't stay politely tucked away. They twist and contort, creating dramatic effects we can actually observe. Picture a valley nestled between two towering mountains. Down in the valley, gravity feels normal, but as you climb, everything gets heavier, as if the mountain slope is warping the very rules of physics. That's the warped throat analogy, a way to visualize how extra dimensions could curve sharply, creating pockets where particles gain wildly different masses. A featherweight particle in one spot might become a heavyweight champion just by sliding along this cosmic terrain. This warping elegantly explains why gravity seems so feeble compared to other forces. It might be leaking into a hidden dimension that's stretched thin, like whispers fading down a long hallway. But here's where it gets wilder. These warped dimensions might not just hide forces, they could create cosmic shortcuts. Think of spacetime as a piece of paper. Normally, traveling from one edge to another means crossing the whole sheet. But fold the paper and suddenly those distant points touch. Warped dimensions could work the same way, bending the fabric of reality to connect far-flung regions of the universe. It's like finding a hidden tunnel under a mountain instead of hiking over it, a potential cheat code for interstellar travel. Physicists Lisa Randall and Raman Sundram first proposed this idea to solve a puzzle: why particles like the Higgs boson are so light compared to the immense energy scales of quantum gravity. Their answer: the Higgs might be trapped in a gentle curve of the warped dimension, while gravity roams the steep slopes, making it seem weaker from our vantage point. It's as if we're living on the calm shore of a lake while tsunamis rage just over the horizon. We only feel the ripples. Could this warping be proven? Experiments at particle colliders hunt for tiny deviations in gravity or unexpected particles that might spill over from these curved dimensions. And if warp-like distortions exist, they could leave fingerprints in gravitational waves, cosmic echoes of hidden geometry. Whether these models hold up or not, they remind us that dimensions might be more like origami than a blank canvas, folded, twisted, and full of surprises. Now let's take a step into one of the most mesmerizing corners of string theory, where extra dimensions aren't just warped but curled up into shapes so intricate they resemble abstract art. These are Calabi-Yau manifolds, the six-dimensional geometric masterpieces that could be hiding right under our noses, governing the very fabric of reality. Picture a tiny, six-dimensional origami, folded so perfectly that it fits into a space far smaller than an atom. That's the essence of a Calabi-Yau manifold. To us, these dimensions are invisible, but in the quantum world, their intricate twists and loops dictate how strings vibrate, and those vibrations determine everything from the mass of an electron to the strength of the forces holding atoms together. Think of it like a cosmic piano. The shape of the Calabi-Yau manifold is the instrument, and the string's vibrations are the notes that compose the symphony of particles we observe. What makes these shapes so special? First, their topology. The way they're connected is mind-bending. Imagine a donut, but not just any donut, one with multiple holes twisted into higher dimensional knots. A Calabi-Yau manifold might have hundreds of holes, each influencing how strings move and interact. The more holes, the more ways strings can vibrate, which means more possible particles. This could explain why our universe has such a rich variety of matter and forces. But here's the catch: there isn't just one possible Calabi-Yau manifold. Physicists have discovered millions, perhaps even billions of these shapes, each with its own unique geometry. This is the infamous landscape problem, an overwhelming zoo of possible configurations, each representing a different universe with its own laws of physics. It's as if nature handed us a catalog of universes and said, pick one. The question is, why this particular shape for our universe? Some theorists suggest it's pure chance, a roll of the cosmic dice in a vast multiverse. Others believe there's a deeper principle we haven't uncovered yet. The implications are staggering. If the Calabi-Yau manifold governing our universe had even slightly different holes or curves, the electron might be heavier, gravity stronger, or chemistry impossible. Life as we know it hinges on the exact vibrational patterns these shapes allow. That's why researchers pore over these geometries, using advanced mathematics and computer simulations to hunt for the one that matches our reality. Could we ever prove these manifolds exist? Direct detection is impossible, they're simply too small, but their fingerprints might show up in particle physics. If we find unexpected particles or symmetries in accelerators, it could hint at the hidden shape of these dimensions. Until then, Calabi-Yau manifolds remain one of the most beautiful and baffling ideas in modern physics, a reminder that the universe's deepest secrets might be written in geometry we're only beginning to understand. Now let's shift our gaze to something even more startling, a theory where dimensions don't just hide but vanish entirely when pushed to extremes. Imagine the fabric of reality simplifying itself under unimaginable pressure, shedding dimensions like layers of an onion. This is the mind-bending premise of vanishing dimensions at high energy, a radical idea that could rewrite our understanding of space-time itself. At everyday energies like those we experience here on Earth, our universe behaves as if it has 3 spatial dimensions plus time. But crank up the energy to levels near the Big Bang, think particle collisions with unimaginable force, and some theorists propose that space-time might collapse into fewer dimensions. Picture an ice cube melting into water. What was once rigid and structured becomes simpler, more fluid. In this case, the complexity of our 4-dimensional space-time might dissolve into a 2-dimensional or even 1-dimensional framework at these extreme energies. Why would this happen? One compelling answer lies in quantum gravity. For decades, physicists have struggled to reconcile Einstein's theory of gravity with quantum mechanics. The math breaks down at the tiniest scales, leading to infinities and paradoxes. But if dimensions vanish at high energies, the equations simplify dramatically. It's like untangling a knot by cutting away the extra thread. Suddenly, the problem becomes solvable. Some models suggest that in these extreme conditions, gravity could behave more like electromagnetism, finally allowing a unified theory of quantum gravity to emerge. But how could we ever test such a wild idea? Cosmic rays, ultra-high-energy particles from deep space, might hold the key. When these particles slam into Earth's atmosphere, they create showers of secondary particles. If dimensions vanish at extreme energies, these cosmic rays could leave behind unusual patterns in their debris, like missing energy or unexpected particle behavior. Experiments like the Pierre Auger Observatory are already sifting through this data, hunting for anomalies that might hint at a dimensional vanishing act. There's another twist. If dimensions disappear at high energies, then the early universe, just moments after the Big Bang, might have been far simpler than we thought. Instead of a roiling, multidimensional chaos, it could have been a near-flat, almost 2-dimensional realm. As the cosmos cooled and expanded, the extra dimensions we know today might have frozen into place like wrinkles forming in a sheet of paper. This could explain why our universe seems so finely tuned. Those hidden dimensions didn't exist at the beginning to complicate things. Of course, this idea is far from proven. Critics argue it's a mathematical trick rather than physical reality. But if future experiments do find evidence of vanishing dimensions, it would revolutionize physics. Suddenly, the vastness of space and the weirdness of quantum mechanics might not be separate puzzles, but 2 sides of the same dimensional coin. It's a reminder that reality, at its core, might be far stranger and simpler than we ever imagined. Now let's explore a radically different approach to understanding hidden dimensions, one where space-time isn't just shrinking or vanishing, but building itself from the ground up. Imagine if the universe were made of tiny geometric puzzle pieces, each simpler than the whole, locking together to create the fabric of reality we experience. That's the heart of causal dynamical triangulation, a theory that suggests space-time might emerge from lower-dimensional building blocks like triangles or tetrahedrons. At the smallest scales, think a million billion times smaller than an atom. This theory proposes that space-time loses its smooth, continuous appearance. Instead, it becomes a patchwork of simple shapes, each representing a tiny chunk of reality. Picture a digital photo, zoom in far enough, and you see individual pixels. In causal dynamical triangulation, those pixels are geometric forms, often triangles in 2 dimensions or tetrahedrons in 3. The magic happens when these pieces interact over time, following strict causal rules to ensure events happen in the right order. As they combine, the complexity grows, eventually giving rise to the 4-dimensional universe we recognize. Here's where it gets wild. At these unimaginably tiny Planck scales, the theory predicts spacetime might behave as if it's effectively 2-dimensional. This isn't because dimensions vanish, as in the high-energy theories we discussed earlier, but because the fundamental building blocks are so simple that they don't yet fill out the full richness of higher dimensions. It's like building a skyscraper starting with flat sheets of metal. The 3rd dimension emerges as you assemble the pieces. Some calculations even suggest that this lower dimensional behavior could explain why gravity appears weak in our everyday world, offering a fresh angle on one of physics' biggest mysteries. How does this stack up against other quantum gravity theories? Unlike string theory, which adds extra dimensions to make the math work, causal dynamical triangulation strips things down to basics. It doesn't require unseen dimensions curled up in Calabi-Yau shapes or floating branes. Instead, it builds everything from minimalist geometric rules. Loop quantum gravity, another contender, shares this bottom-up philosophy but focuses on woven threads of spacetime rather than geometric blocks. Both theories, though, agree on one thing. At the tiniest scales, spacetime is anything but smooth and continuous. The real test, of course, is whether this idea connects to real-world observations. While we can't probe Planck-scale physics directly yet, causal dynamical triangulation makes specific predictions about how spacetime should fluctuate on these tiny scales. Some models suggest these fluctuations could leave faint imprints on the cosmic microwave background, the afterglow of the Big Bang, or even affect how particles behave in high-energy collisions. Future experiments might one day spot these telltale signs, offering a glimpse into the universe's building blocks. What makes this theory so compelling is its elegance. Instead of adding layers of complexity to explain reality, it suggests that complexity emerges from simplicity. The dimensions we take for granted, the stage on which all physics plays out, might not be fundamental at all, but the result of countless tiny interactions over cosmic time. It's a humbling reminder that sometimes the deepest truths come not from looking outward, but from breaking things down to their simplest, most elemental forms. Now let's stretch our imaginations even further into a world where dimensions aren't tidy whole numbers but fractions. You've heard of 3 dimensions of space and 1 of time, but what if reality operates in 3.5 dimensions, or even stranger, somewhere between 2 and 3? Welcome to the mind-bending realm of fractional dimensions, where the very fabric of space might be more intricate than we ever realized. This idea isn't as far-fetched as it sounds. In nature, we see fractional dimensions everywhere. Just look at fractals. A coastline, for instance, isn't a smooth one-dimensional line or a full 2-dimensional plane. Its crinkles and curves give it a dimension somewhere in between, around 1.26. A broccoli floret or a snowflake's branching pattern. They're classic examples of fractal geometry, where infinite complexity unfolds within finite space. Now apply that to the universe itself. What if space-time at its most fundamental level isn't smooth or neatly layered, but instead resembles a fractal with structure at every scale? The implications for physics are staggering. If space-time has fractional dimensions, it could solve some of the deepest puzzles in quantum gravity. Take the quantum foam hypothesis, the idea that at the tiniest scales, space-time bubbles and churns like a turbulent sea. Fractional dimensions might explain why this foam doesn't rip reality apart. Instead of violent, chaotic fluctuations, we'd have a more structured, self-similar chaos like waves repeating at every scale, from the vastness of galaxies down to the Planck length. Some theories suggest that at extremely high energies, like those just after the Big Bang, spacetime's dimensions might have been fractional, slowly crystallizing into the whole numbers we observe today. This could explain why gravity seems so weak compared to other forces. It might be leaking into these in between dimensions, just as water soaks into a sponge's porous structure. Experiments with high-energy particle collisions or precise measurements of gravitational waves could one day reveal traces of this hidden fractional geometry. What's truly fascinating is how this challenges our intuition. We're used to thinking in whole dimensions: a line, a plane, a cube, but nature doesn't always play by our rules. Fractional dimensions blur the boundaries, suggesting that reality might be more fluid, more textured than we ever imagined. Whether this is the key to unifying quantum mechanics and gravity remains to be seen, but one thing's certain: the universe loves a good fractal. And if spacetime is no exception, we might be standing on the brink of a whole new way to see and measure the hidden architecture of everything. Now, let's turn the page to a concept so elegant it feels almost poetic: the idea of mirror symmetry dimensions. Imagine two universes, each with its own unique geometric shape, yet somehow they produce identical physics. This isn't science fiction. It's a cornerstone of string theory known as mirror symmetry, where two seemingly different Calabi-Yau shapes, those intricate six-dimensional spaces we've talked about, turn out to be cosmic twins. Here's how it works. In string theory, the way particles behave depends on how strings vibrate within these curled-up Calabi-Yau spaces. Now, picture two such spaces with completely different geometries. One might have countless holes and twists, while the other looks smooth and simple. Yet, mathematically, they describe the exact same physical laws. It's as if you had two entirely different recipes for baking a cake, but somehow they always produce identical cakes. This mirror duality suggests that the true structure of reality might be deeper than geometry alone, hinting at hidden mathematical dimensions that transcend our usual notions of space. Why does this matter? For one, it reveals a breathtaking flexibility in how the universe could be constructed. If drastically different shapes can yield the same physics, it opens the door to a vast landscape of possible universes, each with its own hidden geometry, yet indistinguishable from others in terms of observable phenomena. This has staggering implications for multiverse theories. If our universe is just one pair in an infinite hall of mirrors, there could be countless mirror versions of reality, each with its own Calabi-Yau shape but governed by the same fundamental rules. But mirror symmetry isn't just a theoretical curiosity. It's a powerful tool for solving real problems in physics. Before this discovery, certain calculations in string theory were impossibly hard on one Calabi-Yau space but straightforward on its mirror. Scientists realized they could swap between the two to crack previously unsolvable equations. It's like having a secret backdoor to the universe's math, a reminder that reality's deepest truths might be hiding in plain sight, just waiting for the right perspective to reveal them. What's truly fascinating is how this challenges our intuition about uniqueness. We're used to thinking that if two things look different, they are different. But mirror symmetry flips that on its head, suggesting that what we perceive as distinct might be two sides of the same coin. Could this mean that dimensions aren't just physical but also mathematical, a kind of hidden code underlying reality? Whether this duality is a quirk of string theory or a clue to something grander, one thing's clear: the universe loves a good symmetry, and if mirror dimensions are any indication, we've only just begun to glimpse the reflections in its cosmic mirror. Now let's venture into one of the most mind-bending ideas yet. What if time itself isn't just a single dimension but multiple? We're used to thinking of time as a straight line, an arrow moving from past to future. But some theories suggest time could branch into higher dimensions, folding and intertwining in ways that defy our everyday experience. Take quantum superposition, for example. In the quantum world, particles can exist in multiple states at once until observed. A cat could be both alive and dead, as Schrödinger famously imagined. But what if this strangeness arises because time isn't linear for these particles? In a model with multiple time dimensions, a particle might not have to choose a single state because it's moving through more than one timeline simultaneously. It's like having several versions of a story playing out in parallel, each with its own thread of time. This ties into the block universe concept where past, present, and future all exist at once, a static four-dimensional block of spacetime. If time splits into higher dimensions, this block could become even more complex, with layers of timelines stacked or woven together. Think of it like a book where every possible outcome is written, but instead of flipping pages sequentially, you're reading multiple chapters at the same time. Then there's the radical two-time physics hypothesis, proposed by physicist Itzhak Bars. This idea suggests that what we perceive as one dimension of time might actually be two, hidden within the equations of our universe. Just as extra spatial dimensions could be curled up too small to see, a second time dimension might be tucked away, subtly influencing physics in ways we're only beginning to unravel. Why consider such wild ideas? Because they might solve puzzles that single-dimension time can't. For instance, quantum entanglement, where particles instantly affect each other across vast distances, could make sense if their connection exists outside our usual flow of time. Or dark energy's mysterious acceleration of the universe might stem from interactions with hidden time dimensions. Of course, testing these ideas is a challenge. How do you detect a dimension of time you can't perceive? Some researchers look for anomalies in particle behavior or gravitational waves that might betray hidden temporal structures. Others explore math for clues, searching for signatures of extra time dimensions in the fabric of reality's equations. Whether time is truly multidimensional remains an open question. But the possibility reminds us that even the most familiar aspects of reality might hold deeper layers waiting to be uncovered. After all, if the universe can hide entire spatial dimensions, why not temporal ones too? The next time you check your watch, remember there might be more to time than meets the eye. Now let's turn our attention to a concept that blurs the line between particles and dimensions: supersymmetry. This elegant framework in theoretical physics suggests that every particle we know might have a hidden, heavier twin. But here's the twist: it also introduces a whole new kind of dimension, one that doesn't behave like the space we're familiar with. Supersymmetry proposes that the universe has extra dimensions, but not the spatial ones we've been discussing. These are called fermionic dimensions, named after the particles they govern, fermions like electrons and quarks. Unlike spatial dimensions, which you could theoretically move through, fermionic dimensions are mathematical beasts based on Grassmann numbers. Picture them as directions where movement isn't measured in meters or miles, but in properties like spin. Grassmann numbers have a quirky rule: if you multiply two of them together, they vanish. That's why these dimensions don't expand like space, they're more like abstract shadows woven into reality's fabric. So why can't we see these dimensions? For starters, they don't interact with light or matter the way spatial dimensions do. Imagine trying to see a shadow cast by a flashlight pointed at a wall. The shadow exists, but it's not an object you can touch. Similarly, fermionic dimensions manifest only in the symmetries between particles, linking boson's force carriers like photons to their hypothetical fermionic twins, photinos, selectrons, and so on. If supersymmetry holds, these twin particles and the dimensions they hint at could be lurking just beyond our current energy scales, waiting to be discovered in particle colliders. The implications are profound. If fermionic dimensions exist, they could explain why gravity is so weak compared to other forces. Perhaps its strength is diluted across these hidden directions. They might also solve the infamous hierarchy problem in particle physics, bridging the vast gap between the mass of the Higgs boson and the energy scales of quantum gravity. Yet supersymmetry remains elusive. Despite decades of searching, colliders haven't found those predicted twin particles. Some theorists argue we might need even higher energies, or that supersymmetry works differently than we thought. Others suggest these dimensions might reveal themselves through subtle cosmic clues, like anomalies in particle decay patterns or gravitational waves. Whether supersymmetric dimensions are real or not, they remind us that the universe's hidden layers might not just be spatial. Some could be woven into the very rules governing particles, invisible yet essential to the cosmos' deepest mysteries. So the next time you hear about particles and forces, remember there might be entire dimensions hiding in the math, waiting to rewrite our understanding of reality. Now let's shift gears to a theory that turns our understanding of dimensions upside down literally. What if the three dimensions we experience every day aren't fundamental at all, but instead emerge from something deeper, like ripples on the surface of a pond? This is the mind-bending premise of emergent dimensions, a concept that suggests space itself, and the dimensions we take for granted might be secondary features of the universe arising from a more basic quantum reality. Think of temperature. We feel it, measure it, and use it daily, but it's not a fundamental property of nature. Instead, it emerges from the chaotic dance of countless atoms and molecules. In the same way, emergent dimension theories propose that space and dimensions might be the result of underlying quantum processes we don't yet fully understand. Imagine zooming in on the fabric of spacetime until you reach the Planck scale, where the smooth geometry we're familiar with dissolves into a seething quantum foam. At this level, dimensions could flicker in and out of existence, only stabilizing into the familiar three-dimensional space we know when viewed at larger scales. One of the most compelling frameworks for this idea comes from loop quantum gravity, a leading contender for unifying quantum mechanics and general relativity. In this theory, spacetime isn't continuous but made of tiny, discrete loops woven into a network. These loops don't exist in space, they are space. The three dimensions we perceive emerge from how these loops intertwine, much like how the two-dimensional surface of a woven tapestry emerges from individual threads. Crucially, this suggests that dimensions aren't static or inherent but dynamic and relational, changing based on interactions at the quantum level. The implications are staggering. If dimensions are emergent, it could explain why we perceive only three spatial dimensions. They might be the most stable configuration arising from the underlying quantum chaos. It might also shed light on the Big Bang. Some models suggest that in the early universe, dimensionality itself could have been in flux, with extra dimensions briefly appearing before collapsing into the structure we see today. Even gravity might not be a fundamental force in this picture, but a side effect of how spacetime's microscopic structure evolves. But how do we test such a radical idea? Experiments are tricky given the scales involved, but subtle signatures might exist. Some physicists look for hints in the cosmic microwave background, ancient light from the early universe that could bear scars of a dimensional transition. Others search for anomalies in high-energy particle collisions, where spacetime's granularity might momentarily reveal itself. There's even speculation that emergent dimensions could leave fingerprints in gravitational waves, tiny ripples that might carry echoes of spacetime's quantum origins. Whether emergent dimensions are real remains an open question, but they challenge us to rethink reality at its core. Dimensions might not be the stage on which the universe plays out. They could be part of the performance, emerging from a deeper symphony of quantum connections. And if that's true, the very fabric of space might be more mysterious, more fluid, and more astonishing than we ever imagined. Now let's venture into one of the most tantalizing possibilities in modern physics. What if the elusive dark matter and dark energy that make up most of our universe aren't just hiding in plain sight, but are actually lurking in dimensions we can't access. This is the intriguing premise behind dark dimensions, a theory that could rewrite our understanding of the cosmos. Imagine our universe as a slice of bread in a vast, multidimensional loaf. Just as you can't see or touch the other slices directly, particles from parallel dimensions might only interact with ours through gravity, the one force that could bridge the gap. This could explain why dark matter, which makes up roughly 27% of the universe, is invisible to telescopes yet exerts a gravitational pull on galaxies. It might not be made of particles we know at all. Instead, it could be matter from another dimension, leaking gravity into ours like ripples passing through a wall. Hidden Valley models take this idea further, proposing entire sectors of particles and forces existing in extra dimensions, completely isolated from our own except for subtle gravitational whispers. These valleys could host exotic forms of matter with their own physics, completely different from anything in our universe. The beauty of this theory is that it elegantly sidesteps the need for new particles in our dimension to explain dark matter. Instead, the mystery could simply be matter from another dimension, forever just out of reach. But how would this solve cosmological puzzles? For one, it could clarify why dark energy seems to be accelerating the expansion of our universe. If extra dimensions are stretching or evolving over time, their gravitational influence on our dimension could mimic the effects of dark energy. Even more intriguingly, it might explain why we haven't detected dark matter particles in underground experiments. They're not here to be found. They're in another dimension entirely, tugging on ours from beyond the veil. Testing this idea isn't easy, but physicists have some clever strategies. Particle colliders could search for missing energy, a telltale sign of particles slipping into hidden dimensions. Gravitational wave detectors might spot anomalies that hint at extra-dimensional influences. Even the distribution of galaxies could hold clues, as structures shaped by hidden dimensions would leave subtle fingerprints in cosmic maps. Dark dimensions remain speculative, but they offer a breathtaking possibility that the majority of our universe isn't just invisible, but exists in realms beyond our perception. If true, it would mean we're not just missing pieces of the cosmic puzzle. We might be missing entire dimensions of reality itself, and that opens doors to discoveries far stranger than anything we've imagined so far. Now let's dive into a concept that bends the very fabric of reality at its smallest scales. Picture spacetime not as a smooth, continuous sheet, but as a bubbling, frothy sea at distances so tiny they defy comprehension. This is the realm of quantum foam, where the fabric of the universe itself churns with fleeting, microscopic dimensions that flicker in and out of existence. At the Planck scale, a distance so small that a single grain of sand contains more Planck lengths than there are grains on all the beaches on Earth, spacetime isn't stable. Instead, it's a turbulent foam of virtual particles, wormholes, and tiny black holes popping into and out of existence like bubbles in a boiling pot. These fleeting structures aren't just random noise. They could represent fleeting extra dimensions, crumpled and twisted into existence by the violent energy of the quantum vacuum. This idea turns our classical understanding of dimensions upside down. Instead of thinking of extra dimensions as fixed, hidden layers, quantum foam suggests they might be dynamic, appearing and disappearing in fractions of a second. These microdimensions wouldn't be large enough to traverse or even detect directly, but their effects could ripple through the fabric of reality. For instance, they might explain the strange behavior of particles at quantum scales, where position and momentum blur into uncertainty. If spacetime itself is frothing with extra dimensions at these scales, it could offer a new perspective on why quantum mechanics seems so counterintuitive. One of the most fascinating implications ties into vacuum energy and zero-point fluctuations. Empty space isn't truly empty, it's a seething ocean of energy, with particles and antiparticles constantly pairing up and annihilating. Quantum foam theories propose that these fluctuations could be tied to the appearance and disappearance of microdimensions. Imagine these tiny dimensions as temporary wrinkles in spacetime, each contributing a minuscule amount of energy to the vacuum. Collectively, they could help explain why the cosmological constant, the energy density of empty space, is so puzzlingly small but not zero. Experimental evidence for quantum foam remains elusive, but physicists have devised clever ways to hunt for its signatures. Some theories suggest that high-energy gamma rays traveling across the universe should arrive at slightly different times if spacetime is foamy, as the fluctuations would subtly alter their path. Others propose that ultra-precise atomic clocks might detect minute variations in timekeeping caused by the foam's turbulence. While we haven't confirmed these effects yet, the search itself pushes the boundaries of how we understand the fundamental nature of reality. Quantum foam dimensions challenge us to rethink not just the architecture of the universe, but the very meaning of dimension. If spacetime is a bubbling, ever-changing foam at its core, our classical notions of length, width, and depth might only be approximations, a smooth average over a far wilder, more dynamic truth. And if that's the case, the hidden dimensions we've been searching for might not be hidden at all. They could be everywhere, flickering in and out of sight, rewriting the rules of physics with every vanishingly brief appearance. Now let's shift gears and venture into one of the most speculative yet fascinating intersections of science and philosophy, the idea that consciousness itself might be tied to hidden dimensions. This isn't just science fiction. Some cutting-edge theories propose that the very fabric of our awareness could arise from structures or processes existing in dimensions beyond the ones we perceive. At the heart of this bold idea is something called orchestrated objective reduction, or ORCH for short, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. This theory suggests that consciousness emerges from quantum processes happening in tiny structures within our brain cells called microtubules. But here's where it gets wild. These quantum processes might depend on, or even interact with higher dimensions. Imagine that our thoughts, feelings, and sense of self aren't just products of electrical signals in our brains, but are somehow entangled with a deeper, multidimensional reality. ORCH ties into panpsychism, the philosophical view that consciousness is a fundamental feature of the universe like space or time. If that's true, then extra dimensions could provide a framework for how consciousness arises and operates. Think of it like this: just as gravity warps the fabric of spacetime, perhaps consciousness warps or interacts with hidden dimensions in ways we don't yet understand. Some interpretations even suggest that these dimensions could explain phenomena like intuition, collective consciousness, or even near-death experiences where the boundaries of our perceived reality seem to blur. Of course, this is highly speculative and ORCH remains controversial in the scientific community. Critics argue that the brain is too warm and noisy for delicate quantum processes to survive long enough to influence consciousness. But proponents counter that the brain's unique environment, its structure, its biochemistry, might create pockets where quantum coherence can thrive, possibly with the help of higher dimensional physics. Another intriguing angle comes from the holographic principle, which we touched on earlier. If our three-dimensional reality is a projection of information encoded on a two-dimensional surface, where does consciousness fit in? Some theories propose that consciousness could be the glue that translates this lower dimensional data into the rich, immersive experience we call reality. In other words, our minds might not just perceive dimensions, they could play an active role in shaping them. While these ideas push the boundaries of both physics and neuroscience, they raise profound questions. Could studying consciousness help us uncover the hidden architecture of the universe? Or might the reverse be true, that unlocking the secrets of extra dimensions could finally explain the mystery of awareness itself? For now, these theories remain at the frontier of science, blending hard physics with deep philosophy. but they remind us that the universe's greatest enigmas, dimensions, consciousness, reality itself, might be far more interconnected than we ever imagined. Moving from the mysteries of consciousness, let's step into a realm where mathematics and reality blur into one, the mathematical universe hypothesis. Proposed by physicist Max Tegmark, this mind-bending theory suggests that every possible mathematical structure isn't just an abstract concept but a real, physical reality in higher dimensions. In other words, if you can describe it with math, it exists somewhere in the multiverse. Tegmark's idea takes the multiverse to its most extreme conclusion. Unlike other theories that propose parallel universes with slightly different physical laws, the mathematical universe hypothesis argues that every conceivable mathematical structure, from simple equations to infinitely complex geometries, corresponds to a genuine physical universe. Imagine a library where every book isn't just a story but an entire cosmos governed by its own unique mathematics. Our universe, with its 3 dimensions of space and 1 of time, is just one volume in that infinite library. This leads us to what Tegmark calls the Level 4 multiverse. Level 1 describes universes like ours but far away in space. Level 2 involves bubble universes with different physical constants. Level 3 is the many worlds interpretation of quantum mechanics, but Level 4, it's where all mathematically possible structures become physical realities. Here, dimensions aren't limited to what we can perceive. Some universes might have 7 spatial dimensions, others none at all. The rules aren't just tweaked, they're entirely rewritten by the underlying math. So how does this connect to hidden dimensions? In Tegmark's framework, the very fabric of reality isn't made of particles or strings, but of pure mathematical relationships. Higher dimensions aren't just curled up or warped, they're mathematical spaces where entirely different laws operate. For instance, a universe with 10 dimensions wouldn't just be our universe plus extras. It might be a reality where gravity behaves inversely or where time loops back on itself in ways our brains can't visualize. Critics argue this idea is untestable or even metaphysical, but Tegmark counters that it's the ultimate simplicity. No arbitrary rules, just math. If true, it means every abstract structure from the Mandelbrot sets infinite complexity to a 5-dimensional hypercube isn't just a human invention but a window into another universe's architecture. Even more intriguingly, it suggests that consciousness or observers like us might emerge in universes where math allows self-aware complexity, a cosmic version of survival bias. The implications are staggering. If every mathematical structure is real, then hidden dimensions aren't just hidden, they're everywhere, in configurations beyond our imagination. It's a universe where the only limit is the boundless creativity of mathematics itself. And that leaves us with a haunting question. Are we discovering math, or is math discovering us? Now, let's shift gears to a theory that bends the boundaries between science and philosophy, the simulation argument. Imagine if our universe, with all its complexity, isn't the base reality but a meticulously crafted simulation running in a higher dimensional computer. This idea, popularized by philosopher Nick Bostrom, suggests that advanced civilizations, possibly in dimensions beyond our own, could be running ancestor simulations so detailed we'd never know the difference. Bostrom's trilemma presents 3 startling possibilities. First, that nearly all civilizations at our level of technological advancement go extinct before becoming capable of creating such simulations. Second, that even if they survive, advanced civilizations lose interest in running ancestor simulations. Or third, the most unsettling option, that we're almost certainly living in a simulation right now. The logic hinges on probability. If future civilizations develop the computing power to simulate conscious experiences, and they choose to run countless simulations, the number of simulated minds would vastly outnumber real ones. Statistically, the odds favor us being one of those simulations, but where do hidden dimensions fit into this? Think of it like this. A simulation powerful enough to mimic our universe would require staggering computational resources far beyond what three-dimensional physics allows. Higher dimensions could provide the processing power needed. In a 4- or 5-dimensional space, for instance, information storage and processing could operate in ways that seem like magic to us. Particles, forces, even the passage of time might be lines of code executed in a substrate we can't perceive. Some theories suggest these higher dimensions could be where the programmers exist, observing or even interacting with our simulated reality from outside our perceptual limits. Critics often dismiss this as unfalsifiable speculation, but intriguing clues have emerged. Ever noticed how the universe operates with mathematical precision? Or how quantum particles behave differently when observed, almost as if the simulation is optimizing resources? Even glitches in physical constants, like tiny variations in the speed of light, have been proposed as potential evidence. Of course, these could just be quirks of nature, but if we are in a simulation, hidden dimensions might be the architecture making it all possible. This theory forces us to confront profound questions. If our reality is simulated, does it make our experiences less real? Could higher dimensions hold the key to breaking the simulation or communicating with whatever lies beyond? Whether you find the idea exhilarating or unsettling, it undeniably redefines how we think about existence itself. After all, in a simulated multiverse, even the concept of hidden dimensions might just be part of the code. Let's take a step into one of cosmology's most mind-stretching ideas: eternal inflation and the bubble universes it spawns. Picture the cosmos not as a single, static entity, but as a frothing sea of universes, each bubble inflating endlessly in a higher dimensional expanse. This theory doesn't just redefine our universe, it suggests an infinite multiverse where hidden dimensions could shape reality in ways we're only beginning to grasp. At the heart of this idea is inflationary cosmology, the notion that our universe underwent a rapid, exponential expansion just after the Big Bang. But what if that inflation never truly stopped? Eternal inflation proposes that some regions of space continue expanding forever, while others pinch off into stable bubbles, each becoming its own separate universe. These bubbles aren't floating in empty space as we know it. They're embedded in a higher dimensional medium called the false vacuum, a metastable state of energy that drives eternal inflation. Think of it like a boiling pot of water where each bubble is a universe and the steam around them is the false vacuum, an unseen scaffold of higher dimensions. Here's where things get wild. The false vacuum isn't uniform. It's a chaotic landscape where quantum fluctuations can trigger new bubbles to nucleate at any moment. And just as bubbles in a sink vary in size and stability, these universes could have wildly different properties, including the number and structure of their dimensions. Some might have our familiar 3 dimensions of space and 1 of time. Others could harbor 4, 5, or even more spatial dimensions, curled up or stretched in ways that make physics unrecognizable. There's even a possibility that the laws of nature, like the strength of gravity or the mass of electrons, are set randomly in each bubble, determined by how dimensions compactify as the bubble forms. This raises a tantalizing question. Could hidden dimensions be the reason our universe seems so finely tuned for life? If an infinite number of bubbles exist, each with random dimensional configurations, it's statistically inevitable that some would, by chance, have the right dimensions and constants to allow stars, planets, and conscious observers like us. In this view, we're not in a special universe, we're in one of the rare, habitable bubbles in a vast higher dimensional foam. Critics argue this is untestable, but clues might lurk in the cosmic microwave background, the afterglow of the Big Bang. Strange patterns or anomalies in this radiation could hint at collisions between our bubble and others, or imprints from higher dimensional physics. Some models even suggest that if we detect certain gravitational wave signatures, it might reveal how dimensions stabilized as our bubble formed. Whether eternal inflation is true or not, it forces us to confront the possibility that our universe is just one tiny pocket in a sprawling, multidimensional metropolis. A place where hidden dimensions aren't just theoretical curiosities, but the very fabric of reality's diversity. And if that's the case, the search for them isn't just about understanding our cosmos. It's about mapping the neighborhoods of a multiverse we've only begun to imagine. Now let's venture into one of the most enigmatic corners of cosmology, black holes and their possible connection to hidden dimensions. Imagine crossing the event horizon, not toward destruction, but into a gateway. Some theories suggest that the crushing singularity at a black hole's heart might not be an end, but a doorway to entirely new dimensions or even parallel universes. This idea traces back to Einstein and Rosen, who in the 1930s proposed what we now call Einstein-Rosen bridges, mathematical tunnels linking distant points in spacetime. Today, we know them as wormholes, but their original formulation hinted at something deeper. If you fell into a black hole, conventional physics says you'd be torn apart by tidal forces. But in some models, the singularity might act like a cosmic portal, warping spacetime so severely that it opens a passage to another realm. These bridges could connect not just different places in our universe, but entirely separate universes with their own sets of dimensions. Then there's the wild card, white holes. Theoretically, these are the opposite of black holes, spewing out matter and energy rather than devouring it. Some physicists speculate that a black hole's interior might funnel into a white hole in another universe, creating a one-way tunnel between realities. If true, this could mean that what we perceive as a black hole's destructive power is actually a recycling mechanism for spacetime, with matter and energy emerging somewhere else, possibly in a universe with different physical laws or extra dimensions. But here's where things get even stranger. The information paradox, a long-standing puzzle about whether information swallowed by black holes is truly lost, might find its resolution in hidden dimensions. Quantum mechanics insists information can't be destroyed, yet black holes seem to erase it. One proposed solution is that information isn't destroyed but encoded in higher dimensional structures within the black hole, or even ejected into another universe through a white hole. If so, dimensions beyond our own could be the key to preserving the universe's quantum rulebook. Could we ever test these ideas? Some researchers suggest that microscopic black holes, if created in particle colliders or detected in cosmic rays, might reveal traces of extra dimensions through their decay patterns. Others look for gravitational wave signatures that deviate from expectations, which could hint at hidden dimensional geometries near black holes. Whether black holes are cosmic shredders or interdimensional gateways, they force us to confront the limits of our understanding. If their singularities truly open into new dimensions or universes, it would mean that the most destructive objects in the cosmos might also be the most creative bridges to realities we've yet to imagine. And that's a thought as thrilling as it is humbling. Now let's take a cosmic leap into one of the most mind-bending ideas about the universe's hidden depths: conformal cyclic cosmology, a theory proposed by the Nobel Prize-winning physicist Roger Penrose. This isn't just another take on the Big Bang. Instead, Penrose suggests that our universe's story isn't a one-time event but part of an endless cycle of rebirth, with hidden dimensions playing a crucial role in the process. Here's how it works. Imagine the universe not with a definitive beginning or end, but as a series of epochs, each stretching into eternity. In Penrose's model, when our universe reaches its far future, a cold, dark expanse where black holes have evaporated and particles have drifted apart, it doesn't just fade into oblivion. Instead, it undergoes what's called a conformal rescaling. This is a mathematical transformation that essentially resets the universe, stripping away all scale and leaving only its fundamental shape. At this point, the universe becomes smooth and featureless, indistinguishable from the conditions right before the Big Bang. And just like that, a new cycle begins. What makes this theory so fascinating is how it ties into the mystery of entropy, the measure of disorder in the universe. Normally, entropy always increases, leading to the so-called heat death, where energy is evenly distributed and nothing interesting happens anymore. But Penrose argues that at the crossover point between cycles, entropy resets to zero. The universe forgets its past disorder, allowing a fresh start. This idea sidesteps the entropy problem that plagues other cyclical models, where each new cycle would theoretically start with more chaos than the last. But where do extra dimensions come in? Penrose's framework hints that these cyclical rescalings might involve higher dimensional geometry. The conformal transformation could be a kind of higher dimensional folding of spacetime, where the universe's information isn't lost but preserved in a form we can't yet perceive. Some versions of the theory even suggest that gravitational waves from previous universes might leave imprints in the cosmic microwave background, subtle ripples that could be evidence of dimensions beyond our own. Could we ever test this? Penrose and his collaborators claim they've found these imprints patterns in the cosmic microwave background they call Hawking points, possibly remnants of black holes from a prior universe. If confirmed, this would be groundbreaking evidence not just for cyclic cosmology, but for the idea that dimensions and information transcend individual cosmic cycles. Whether or not Penrose's vision holds up, it forces us to rethink the universe's timeline. Instead of a single explosive beginning, we might be part of an endless loop of creation and transformation, with hidden dimensions serving as the silent architects of reality itself. It's a humbling thought, one that turns the Big Bang from a singular event into just one note in an infinite cosmic symphony. Now let's shift our perspective to an even grander cosmic stage, bulk cosmology, where our entire universe might just be one slice of a much vaster, higher dimensional reality. Think of it like this: if our universe were a sheet of paper, the bulk would be the entire room it's floating in, with dimensions we can't see but whose influence might be all around us. This idea isn't just science fiction. It builds on the Brane World Scenario we discussed earlier, but takes it to a mind-bending scale. In bulk cosmology, our four-dimensional space-time, 3 dimensions of space plus time, is embedded within a higher dimensional space called the bulk. Other universes, or even different regions of our own, could coexist in this bulk like parallel sheets of paper suspended in air. The forces we experience, like gravity, might leak into or out of these extra dimensions, explaining mysteries that standard physics struggles with. One of the biggest puzzles bulk cosmology could solve is dark flow, a strange phenomenon where clusters of galaxies appear to move in a coordinated direction at speeds that shouldn't be possible under known physics. Observational data from galaxy surveys suggest something massive outside our observable universe is tugging on them. Could this be the gravitational pull of another universe or structure in the bulk? It's a tantalizing possibility. Then there's dark matter. If some of it exists in higher dimensions, its gravitational effects would still reach us, but we'd only perceive it as mysterious missing mass. Similarly, dark energy, the force accelerating the universe's expansion, might arise from interactions with the bulk itself. Some theories suggest the bulk could act like an elastic medium, pushing our universe apart as it stretches or vibrates. The implications don't stop there. If the bulk exists, it might offer shortcuts through space-time wormholes or bridges between distant points in our universe, or even gateways to others. These wouldn't be the sci-fi tunnels you might imagine, but natural folds in higher dimensional geometry. Testing these ideas isn't easy, but physicists have proposed ways to look for clues. Tiny ripples in gravity waves, anomalies in particle collisions, or even subtle patterns in the cosmic microwave background could hint at the bulk's existence. Some experiments aim to detect gravitons, the hypothetical particles carrying gravity leaking into extra dimensions, which would appear as missing energy in particle detectors. Bulk cosmology turns the universe into something far richer and stranger than we once thought. It suggests we're not just living in a cosmos, but within a cosmos, one layer of a reality with depths we're only beginning to imagine. Whether or not the bulk is real, the theory challenges us to think bigger, pushing the boundaries of what the universe might truly be. Now let's zoom in on something even more fundamental. Why do we experience only 3 dimensions of space and 1 of time? Quantum Darwinism dimensions might hold the answer, suggesting that the dimensions we perceive are the ones that survive a kind of cosmic natural selection. Here's how it works. In the quantum world, particles exist in many possible states at once, a phenomenon called superposition. But when these particles interact with their environment, say, through collisions or even just exposure to light, they decohere, collapsing into a single observable state. This is why we don't see macroscopic objects in superposition, like cats being both alive and dead. Quantum Darwinism takes this further, proposing that decoherence doesn't just pick which quantum states we see, it might also determine which dimensions become real to us. Imagine a bustling marketplace where countless vendors are shouting their wares, but only the loudest, most persistent voices reach your ears. Similarly, out of all possible dimensions, the ones we perceive, the 3 spatial and 1 temporal, could be the ones that shout the loudest through decoherence. The other dimensions, if they exist, might remain hidden because they decohere too quickly or don't interact strongly enough with our environment to leave a lasting imprint. This idea ties into why our universe appears so stable and classical at large scales. If extra dimensions were constantly fluctuating or interacting unpredictably, they'd be wiped out by decoherence, leaving only the most robust dimensions standing. It's like how only the sturdiest structures survive a storm. The others collapse into obscurity. Some scientists speculate that this could explain why gravity seems so weak compared to other forces. If gravity leaks into dimensions that have decohered away, its effects would be diluted in our perceivable reality. This would neatly connect quantum Darwinism to some of the other theories we've discussed, like large extra dimensions or brane worlds. But how could we test such a mind-bending idea? One clue might come from the cosmic microwave background, the afterglow of the Big Bang. Subtle patterns in this radiation could reveal traces of decoherence acting on early spacetime. Another avenue is lab experiments with ultra-cold quantum systems, where scientists can simulate how decoherence shapes reality. If certain dimensions consistently emerge as classical, it would lend weight to this theory. Quantum Darwinism dimensions offers a radical yet elegant explanation for the structure of our reality. It suggests that what we perceive isn't just a quirk of biology or physics, but the result of a deeper, almost evolutionary process, where the dimensions we experience are the ones that won the battle for persistence. Whether or not this theory holds, it reminds us that the universe's hidden layers might be shaped by rules we're only beginning to uncover. Now let's shift our focus to another fascinating intersection of dimensions and cosmic mysteries: holographic dark energy. This theory suggests that dark energy, the mysterious force accelerating the universe's expansion, might be deeply connected to extra dimensions through the holographic principle. Imagine the universe as a cosmic hologram, where all the information about our 3-dimensional reality is somehow encoded on a 2-dimensional surface at its boundary. This mind-bending idea, born from string theory and black hole physics, implies that extra dimensions could play a crucial role in shaping the energy density of space itself. Here's where dark energy comes in. Observations show that empty space isn't truly empty. It crackles with vacuum energy, a kind of background hum that permeates everything. But there's a problem. When physicists try to calculate how much energy this vacuum should contain, their predictions are off by a ludicrous factor of around 1 followed by 120 zeros. This embarrassing mismatch, known as the cosmological constant problem, suggests we're missing something fundamental about how space stores energy. Holographic dark energy offers a potential solution by tying vacuum energy to the number of dimensions in the universe. The theory proposes that the energy density isn't determined solely by our familiar three spatial dimensions, but by how information is spread across all dimensions, including hidden ones. It's like realizing the volume of a library depends not just on the size of its rooms, but on how efficiently its books are shelved across multiple floors we can't see. This approach dramatically changes the math. Instead of vacuum energy depending on the tiny Planck length, about 10 to the power of -35 meters, holographic dark energy links it to the much larger cosmic horizon, the farthest distance light could have traveled since the Big Bang. This shift in scale brings predicted energy densities much closer to what we observe, potentially solving the cosmological constant puzzle. But how do extra dimensions fit in? The holographic principle suggests that higher dimensional spaces can encode information more efficiently, like compressing a three-dimensional movie onto a two-dimensional Blu-ray disc. If dark energy emerges from this cosmic data compression, then the number and nature of extra dimensions would directly influence its strength. Some models even propose that dark energy's acceleration could be a side effect of information spreading into these hidden dimensions over time. Testing this idea isn't easy, but astronomers are looking for subtle changes in how dark energy behaves as the universe ages. If its density evolves in ways that match holographic predictions, it could point to extra dimensions shaping reality from behind the scenes. Other clues might come from gravitational waves, which could carry fingerprints of higher dimensional effects as they ripple through space-time. Holographic dark energy beautifully marries two of physics' biggest puzzles, the nature of dark energy and the existence of extra dimensions. It suggests that the accelerating expansion of our universe might not just be about what's happening in the dimensions we see, but about how reality organizes itself across all dimensions, seen and unseen. Whether this theory holds up or not, it reminds us that the cosmos often hides its deepest secrets in the connections between seemingly unrelated phenomena. Moving beyond natural phenomena, let's consider what might happen if intelligence learned to harness extra dimensions. The idea of dimensional engineering takes our exploration from theoretical physics into the realm of hypothetical future technologies, where advanced civilizations might bend hidden dimensions to their will. Picture a civilization millions of years more developed than ours. With mastery over extra dimensions, they could achieve feats that look like magic to us. One tantalizing possibility is the Alcubierre drive, a concept grounded in Einstein's equations that could allow faster-than-light travel without breaking relativity. Here's how it might work with extra dimensions. Instead of moving through ordinary space, a spacecraft could create a warp bubble by manipulating higher dimensional spacetime. The ship would compress space in front of it and expand space behind, riding this distortion like a surfer on a wave. Extra dimensions could provide the room needed to twist spacetime in ways our three-dimensional perspective can't accomplish. Then there are traversable wormholes, cosmic shortcuts connecting distant points in space. While naturally occurring wormholes would likely be unstable, an advanced civilization might stabilize them using exotic matter with negative energy, possibly harvested from higher dimensions. Some theories suggest that extra dimensions could make wormhole engineering more practical by providing additional pathways for stabilizing these spacetime tunnels. Imagine stepping through a portal in New York and emerging near a star system light years away, all because some ingenious beings figured out how to stitch together different dimensional fabrics. But dimensional engineering could go even further. Higher dimensions might offer new ways to store and process information. A hyperdimensional computer could perform calculations impossible in our limited 3D framework, solving problems in moments that would take conventional computers millennia. Energy extraction is another frontier. What if dark energy or other higher dimensional phenomena could be tapped as power sources? The energy density of extra dimensions, if accessible, could provide limitless clean energy without the need for stars or fossil fuels. Of course, these speculations raise profound questions. Would manipulating extra dimensions create detectable signatures? Some physicists suggest that advanced dimensional engineering might leave traces in gravitational wave patterns or cosmic microwave background radiation. There's even the eerie possibility that we're living in an artificially constructed dimensional framework without realizing it, like characters in a simulation unaware of their programmers. While dimensional engineering remains firmly in the realm of speculation today, it stretches our imagination about what might be possible. From warping spacetime for interstellar travel to building computational networks in higher dimensions, the potential applications remind us that extra dimensions aren't just abstract mathematical concepts. They could be the next frontier for intelligence in the cosmos. Whether humanity will ever reach such capabilities remains unknown, but the mere possibility invites us to reconsider our place in a potentially multidimensional universe. Now let's take a mind-bending turn into one of the most intriguing possibilities. What if the universe itself is conscious, and extra dimensions are the key to that consciousness? This theory pushes the boundaries of both science and philosophy, suggesting that awareness might not be confined to biological brains but could be woven into the very fabric of reality. At the heart of this idea is integrated information theory, which attempts to explain how consciousness arises from complex networks of information. The theory proposes that any system with a high enough degree of interconnectedness and information integration can possess some level of awareness. But here's where extra dimensions come in. What if the substrate for this universal consciousness exists beyond our familiar 3 dimensions? Higher dimensions could provide the necessary complexity for information to integrate in ways we can't even perceive, allowing the universe to think on a cosmic scale. Think of it like this: your brain is a 3-dimensional structure, but its neurons form networks so intricate that they give rise to your thoughts and experiences. Now imagine the universe as a vastly more complex version of that, with hidden dimensions enabling connections and computations far beyond what our 3D perspective can grasp. Some researchers speculate that dark matter or dark energy, which we still don't fully understand, might play a role in this higher dimensional consciousness, acting as the unseen neurons of a cosmic mind. This line of thinking also dovetails with panpsychism, the view that consciousness is a fundamental property of reality, present even at the most basic levels. If that's true, then extra dimensions could be the scaffolding that allows simple forms of awareness to scale up into something universal. Just as gravity emerges from the curvature of spacetime, perhaps self-awareness emerges from the interplay of hidden dimensions we're only beginning to theorize about. But the most provocative question remains: if the universe is conscious, what does that imply about us? Are we isolated pockets of awareness, or are we interconnected nodes in a grander cosmic mind? Some theories even suggest that human consciousness could be a localized expression of this universal awareness, like waves rising from an unfathomably deep ocean of higher dimensional thought. Of course, this is highly speculative, but it forces us to confront profound mysteries. How would we test such a theory? Could certain patterns in quantum mechanics or cosmology hint at a universe processing information in extra dimensions? Whether you find this idea electrifying or unsettling, it undeniably reshapes how we view our place in existence, not just as observers of the cosmos, but potentially as participants in something far more vast and mysterious. Now let's push even further into the cosmic unknown with the most daring idea of all. What if every possible universe exists, each with its own unique set of dimensions? This is the ultimate ensemble theory, a mind-stretching concept suggesting that reality isn't just one universe with hidden dimensions, but an infinite collection of every conceivable configuration of space, time, and beyond. Picture a cosmic library where every book is a universe with its own rules, some with 4 dimensions, others with 10, or even stranger geometries we can't begin to imagine. At the heart of this idea is the mathematical multiverse, championed by physicist Max Tegmark. He proposes that every mathematically consistent structure must physically exist somewhere in the grand ensemble. If a set of dimensions can be described by equations without contradictions, then it's out there, real and tangible, in some corner of the multiverse. This means our universe, with its 3 spatial dimensions and 1 of time, is just one tiny volume in an unfathomably vast landscape of possibilities. What makes this theory so radical is how it swallows all the others we've discussed. Brane worlds, they're in there, cyclic dimensions, those too. Even the consciousness-infused universes we just explored, they're all part of the ultimate ensemble. It's like realizing every theory we've ever debated isn't competing for the right answer, but simply describing different neighborhoods in a multiverse too big for any single idea to contain. But here's the kicker: if every possible universe exists, how do we explain why this one feels so real to us? One answer lies in anthropic reasoning. We can only perceive a universe compatible with our existence. A cosmos with too few dimensions might not allow for complex structures like stars or branes, while one with too many could dilute gravity so much that planets never form. Our 3-dimensional experience isn't special, it's just the only slice of reality where beings like us could arise to ponder it. Critics argue this theory borders on metaphysics, since it's nearly impossible to test. But supporters point to eerie fine-tuning in our universe's constants like the strength of gravity or the mass of electrons as indirect evidence. If all configurations exist, of course we'd find ourselves in one where life is possible, no matter how statistically unlikely. It's the ultimate cosmic shrug. Everything that can exist does. So where does that leave us? Either we're living in a breathtakingly rare universe finely tuned for life, or we're one thread in an infinite tapestry of realities, most of which would seem utterly alien to us. Either way, the ultimate ensemble theory doesn't just expand our notion of space, it redefines existence itself. And if that doesn't make you pause next time you look at the night sky, nothing will. As we wrap up this journey through the hidden layers of reality, let's take a moment to marvel at the sheer variety of ideas we've explored. From the tightly curled dimensions of string theory to the infinite possibilities of the ultimate ensemble, each theory offers a unique window into the cosmos' deepest secrets. What's truly astonishing is how these concepts blur the line between science and philosophy, challenging us to rethink not just the universe's structure, but the very nature of existence itself. Some theories, like the Holographic Principle or Brane World Scenario, emerge from rigorous mathematics, while others, like consciousness dimensions, venture into uncharted territory where physics meets metaphysics. Yet all share one thing: they push human imagination to its limits. Whether it's the elegant geometry of Calabi-Yau manifolds or the mind-bending notion that time could split into multiple dimensions, these ideas remind us that reality might be far stranger than we ever dared to suspect. Now, here's where you come in. Which of these theories resonated with you the most? Was it the haunting elegance of the holographic universe, or the thrilling possibility of parallel worlds just beyond our perception? Drop your thoughts in the comments. Let's keep this cosmic conversation going. After all, the most exciting part of science isn't having all the answers, but daring to ask the questions that stretch our understanding. So as we close, consider this: if hidden dimensions do exist, weaving unseen through the fabric of our everyday lives, what does that say about the true nature of reality? Are we just scratching the surface of a deeper truth, or is the universe's ultimate mystery something no equation will ever fully capture? The night sky has never held so many secrets or so much wonder. If these ideas left your mind buzzing, don't forget to hit that like button and subscribe for more deep dives into the universe's greatest mysteries. Tap the bell so you never miss an exploration into the unknown. Until next time, keep looking up and questioning everything.